Hello, everyone. This episode of the Michael Shermer Show is brought to you by Brilliant. Brilliant is an online platform that I've been using for quite a while now. I really enjoy it, and you would too. Go to brilliant.org/skeptic, and you will get a free 30-day trial, and the first 200 of you will get 20% off the annual subscription. What is it? It's a subscription to a learning/teaching platform with easy-to-follow lessons. Even a non-physics person like me can take a lesson. I've been doing the astrophysics course and lessons on gases and solids and liquids, gravity and how it works. This one is on the flat Earth. This is really relevant because we've debunked the flat earthers here. But how do you know that the Earth is not flat? And so they explain how we know on this easy-to-do lesson, and then they give you a little quiz. The circular shape of the Earth's shadow seems like irrefutable evidence for a spherical Earth. But is this observation robust to flat earther scrutiny? So, yes, a round shadow could only be observed with a spherical Earth, or no, a round shadow could be observed with a flat Earth. I'm going to put the second one there because, and I'm correct, because the Earth could be round and flat like a pizza. And if it happened to be like this, casting a round shadow on the moon during an eclipse, then that would not disprove the flat earthers. That's how they think. But it's a great teaching tool for going through simple things like that. So check it out. Go to brilliant.org/skeptic to get your free 30-day trial. And the first 200 of you that log in will get 20% off the annual subscription rate. Check it out, brilliant.org/skeptic. All right, here's our episode. Okay, my guest today, the returning champion, Dr. Paul Halpern, is the author of 18 popular science books exploring the subjects of space, time, higher dimensions, dark energy, dark matter, exoplanets, particle physics, and cosmology. The recipient of a Guggenheim Fellowship, a Fulbright Scholarship, and an Athenaeum Literary Award. He has contributed to Nature, Physics Today, Aeon, Nova's The Nature of Reality, Physics Blog, and Forbes Starts with a Bang. I'm guessing that has to do with the Big Bang, as well as on Friday, Science Friday, and Radio Times, and so on. Oh, he's also been on Coast to Coast, AM, one of my favorite conspiracy and UFO shows. Let's see. He's also appeared previously on the show for his book, Synchronicity, The Epic Quest to Understand the Quantum Nature of Cause and Effect. Here's the new book, The Allure of the Multiverse. It describes the controversial history of higher dimensional and parallel universe schemes in science and culture. And you can read more about this at allureofthemultiverse.com. That's at the Allure of the Multiverse. Okay, Paul, nice to see you again. How you doing?
Hi, Michael. Thanks for having me back again.
So what's the are there new findings here, or is this just a new subject for you that you got interested in addition to your previous works?
Well, it's become such a popular interest recently with all the films out there about the multiverse and TV series. Loki season 2 has been very popular. What If, Everything Everywhere All at Once. It just seems like we're being bombarded with popular images of the multiverse. And in terms of findings, it just seems that in recent years, I guess in past couple of decades, there have been more and more prominent figures who've come out and said, look, it would be good if we could solve all the problems in physics in our own universe, but perhaps we should be open-minded and consider the possibility that our universe is one of an ensemble of other universes out there, as strange as it sounds, and also as, in a way, not perfect in terms of in trying to make observations of everything. In theory, we would like to be able to observe everything in the universe, but in practice, there may be aspects of the universe or even other universes that might remain outside of observability.
Oh, interesting. So if we do a kind of a epistemological breakdown via Donald Rumsfeld, we have the known knowns, the things we know. Then there's the known unknowns, the things we know we don't know, but we will know. Are you suggesting that there's known unknowables, that they're just things we may never be able to get at?
Well, I think there are definitely things that we can never get at, even if we don't believe in the multiverse, just because of the speed of light. So all of our information is bounded by this speed limit in space. And the fact is that we can only pick up signals from a radius within light can reach us. If light cannot reach us and no other signals can reach us, then pretty much we're stuck not knowing about those things.
Yeah. So then what makes us think that there is such a thing as a multiverse? And let me tee it up this way. I like the idea because it's sort of the natural extension. Here's what I wrote. I was working on my chapter in my next book using your book. Anyway, finally, from what we now know about the cosmos, universe, multiverse, or whatever it turns out to be, to think that this is all this was created for just one species among tens of millions of species who live on one planet circling one of a couple 100 billion stars that are located in one galaxy among hundreds of billions of galaxies, all of which are one universe among perhaps an infinite number of universes, all nestled within a grand cosmic multiverse, is provisionally insular and anthropocentrically blinkered. It's not all about us. Now, the reason I wrote that is because theists will say, well, you got to take the causal chain back and stop it somewhere. We stop at God. And, the fine-tuning argument and all that stuff. So we counter with, well, the multiverse. There's multiple universes. They have different laws of nature, and we just happen to be in one of those. And they go, that's your faith. You don't know, and you'll never know. That's no different than our faith. And so we're both faith-based. How do you respond to something like that?
Well, I've interviewed for my book so many different prominent figures, from Nobel Prize winners to prominent astrophysicists. And I was kind of surprised by the reaction. Some people, of course, were absolutely against the idea of the multiverse. The late Stanley Deser, who was prominent in supergravity and all sorts of things that are undetectable, sent me an email back and said he was kind of in his, as it turns out, his final months of life. He lived into his 90s, and his email was just, there's enough, and I'm going to use a word from Yiddish, enough tsuris in our universe to deal with. So he meant enough, it means enough pain or woe. And in our universe, why consider other universes? On the other hand, Virginia Trimble, prominent astrophysicist, whose specialty has been observable things and observation time on telescopes and making reaching conclusions based on those, was very quick to say, look, every time we wondered about things that are out there that we don't observe, they've turned out to be correct, starting with beyond the solar system. Are there other stars? And then now we know that there are planets around other stars. We couldn't observe them in our lifetime. When I was a kid, everybody said 9 planets. And now they say thousands of planets and, likely trillions of planets. We just can't see all of them. So every time we've speculated about things and said, well, what if something else is out there? Not every time, but a lot of times we speculate about things. It's turned out to be true. So I try to remain open-minded, especially because figures such as, Steven Weinberg, the late Nobel laureate, was very open to the idea of a multiverse and, in fact, advocated it and caused a lot of controversy that way. So it is a controversy, but the fact is there's so many things in physics now that are not directly observable, and things that we take for granted, such as the idea of the strong force and the weak force. We don't directly detect those with our senses. We use models, and the models all point to the idea of these two forces in atomic nuclei, and we all believe in it, even though we don't directly experience those forces. So there are a lot of things in physics that are indirect observations. Plus, quantum mechanics tells us that we can't observe everything at once, and that everything is based on these abstract entities called quantum states, which we can never directly observe. So there's just so much that is not directly observable. The question is, do we exclude the idea of universes themselves that are not directly observable? And that's an open question. And I respect both sides of that argument.
Yeah. Yeah, it reminds me of the Copernican principle that we're not special. If you apply that to everything, that does make sense for planetary formations, assuming planetary formations are a natural process like we have in our own, then they should be all over the place. And in fact, they are. So that would be one of those inferences that then turns out to be testable and tested positive in that sense. So why not expand that to galaxies and then universes? If universes are born out of, let's say, collapsing black holes or some such thing, I don't know what I'm talking about when I say this, so you can elaborate on that. But something about collapsing to a singularity and out pops another bubble universe or some such thing, then universes should be naturally forming all over the place.
Yes.
Or something like that.
Yes, that's interesting. You're talking about Lee Smolin's hypothesis. Lee Smolin talked about an evolution of universes. But Lee, as far as I know today, is not interested in ideas of higher dimensional realities or string theory and so forth, which is fine. But I find that a lot of physicists have their own hypotheses, their own hypothetical ideas that might not be directly testable, but then look at other theories and say, hey, wait a minute, we need testability for those theories. So if we apply the same standard that you need all theories to be directly testable, then that would really narrow down a lot. And you would be back to Einstein's conclusion that everything should be deterministic, everything should be local, everything should have an objective reality. And we know from quantum mechanics that that can't possibly be true because we have these wave functions or quantum states that are out there that we don't measure except through indirect measurements, not directly measuring these quantum states.
Are there truths to be derived just through mathematics where you could say, for example, the multiverse comes out of the equations, even if it's not presently testable, there's good reasons to believe it's true because of the whatever mathematical elegance or power or beauty or something like that?
Yes, well, that is an argument that's made, and it's fascinating that Albert Einstein, in developing the general theory of relativity, did not base his arguments initially on testing observability or anything like that. He came up with a theory that satisfied certain mathematical and logical principles, and that turned out to be the case. And general relativity predicts that the universe should be infinite. If it's flat, it should be infinite, according to general relativity. Now, we can never prove that. How can you prove that something is infinite? And we have a radius of observation in our universe beyond which telescopes cannot detect, and that is about 46 billion light years in radius. So beyond that, we just assume, okay, if the universe has a flat geometry, meaning kind of like a box extended in all directions, in our enclave, we assume that that's going to continue beyond the observable. But someone could say, hey, wait a minute, we don't know what's out there, so the universe could just end beyond observability. We can't prove it one way or the other. We just assume it based upon the mathematical idea of continuity, that we expect that if something is true within our observable universe, it probably is true, at least for a certain region beyond that.
You mentioned 46 billion years. Could you explain how you get that number? Because the universe is 13.8 billion years old, right? So if we're in the center, as it were, in terms of observations, wouldn't it just be double that? Then 27, something, or 20, close to 28 billion years would be the total. I don't know what the diameter or the radius of the sphere.
That's an excellent question. And the question is, why is the observable universe so big today? It has to do with the expansion and, in fact, the accelerated expansion of the universe. So it's a little bit like if a football player is standing still and throwing you a football, you can kind of estimate their distance, and you know that they're a certain distance away based upon the speed that they throw the football. But then if you said, well, what if they're running away from you at a super high speed and they throw the football at you and then they run away from you at an extraordinary speed, and you say, oh, well, they must be about 10 feet away because their speed is about 10 feet per second, and it took about a second for me to get the football. But in fact, they could be much farther away than that because they are running away from you. Similarly, all of the galaxies are running away from us. So they send off light. That light starts traveling toward us. And then meanwhile, the galaxies are moving extremely far away. So in a sense, we can see galaxies that are well beyond this 13.8 billion light year radius because they've moved so much further away from us that we know that they're out there, and that greatly increases the size of the observable universe.
I see. Now, in a Big Bang explosion, explosions slow down. I mean, explosions on Earth anyway. The energy dissipates and so on. Why is the explosion expansion accelerating?
Well, that is a big question. So if there wasn't something called dark energy, which is a mysterious substance that acts as a kind of anti-gravity, then the universe would eventually start slowing down, or it would have been slowing down already. But amazingly, in 1998, two teams of researchers looking at distant supernova discovered that the universe is in fact speeding up in its expansion. And because it's speeding up in its expansion, it's never going to slow down as far as we know, unless it does, about face at a certain point. But it's going to just keep expanding forever as far as we know. So that is a real big mystery. And the question is, what causes this dark energy? What causes this anti-gravity? And one model for it is to imagine something called a cosmological constant, which is a term that Einstein originally proposed to stabilize the universe, but then eventually discarded. But then after 1998, physicists such as Michael Turner and others revived the idea of the cosmological constant and said, well, there's something out there which is pushing the universe faster and faster away from each other. The galaxies faster and faster away from each other, expanding the universe faster and faster. But we don't know what it is. And strangely enough, vacuum energy, which is the energy of all the particles flitting in and out of empty space, also has an effective cosmological constant. You can estimate that. And that's incredibly higher than the cosmological constant needed to propel the universe's accelerated expansion. And that's one of the big mysteries. Why is the cosmological constant that we measure through expansion and its acceleration so much lower than the cosmological constant that we estimate by all the energy out there in the universe that we know about? And that's where one idea for a multiverse comes in. We say, well, maybe we're an outlier. Maybe we're a really, really, really unusual universe. And there's an ensemble of universes out there with all different cosmological constants. And some of them are really, really high. Some of them are medium. And we happen to have the baby, low cosmological constant. We just happen to be in a universe with a tiny cosmological constant, because that way the universe's expansion could remain fairly constant for a while. And that would lead to galaxies, stars, planets, and life as we know it. And if we didn't have a tiny cosmological constant, we wouldn't be talking today. We'd be in a universe that exploded in acceleration and size billions of years ago, and nobody would be here to talk about it.
You're right. Something like the Anthropic principle there, at least the weak version of that we have to be in this kind of universe or we wouldn't be here talking about it.
Yes, exactly.
Yeah, so like on the again, like on the cover of your book, you have these bubble universes, or I think that's what they're supposed to be, and that would sort of correspond to the Lees-Mollins model that we talked about earlier, where these little bubbles are erupting. There's new big bangs out of collapsing black holes, or whatever it is. But so explain that. How did they not collide with each other, or could they collide with each other, and you'd get some kind of ripple effect from gravitational waves, and you could detect them, or some such thing? Where are they expanding into?
Well, the idea of baby universes from black holes is a viewpoint held by a handful of physicists. More prominently is the viewpoint of Andre Linde, who developed what is called eternal inflation. And inflation is a model designed to smooth out the universe by having a period in its early history of ultra rapid expansion, very, very fast, trillionth of a second or less era of ultra rapid expansion. And to trigger that, Andre Linde found that if you had a special type of energy field, you could easily trigger that in the early universe or any time in the universe. And it's just very, very easy to trigger. You just have to have a special type of energy field, which is very, fairly easy to produce. And Andre Linde soon thereafter discovered that because it's so simple to produce this trigger for super rapid expansion, inflation must happen, ubiquitously, all the time, everywhere, and there must be a sea of bubble universes. So you don't need black holes necessarily to produce these bubble universes. You could have a completely empty universe, a vacuum universe, but just through quantum randomness, a scalar field just is a technical term for a field that has a single value at every point in space, emerges. And if it has a certain property, it will suddenly trigger that region to experience ultra rapid expansion, and that region will become its own universe.
The empty vacuum universe. So where's the stuff that bangs? Where does that come from?
Well, you start, let's say, with a singularity. That would be the Big Bang. And at that point, you have this expanding universe, but you don't really have much material in it. But in any kind of vacuum, according to quantum physics, the uncertainty principle says that something can arise from nothing if you have a small enough quantity of it, and if it pops in and out rapidly enough. So it's Heisenberg's principle that the uncertainty in energy times the uncertainty in time is a very small number. So if you have a bit of energy that exists for a fleeting moment, it can just pop out of nothing. And the uncertainty principle says that's perfectly valid to have that violation of conservation of energy as long as it happens briefly. But if you have this energy popping out of nothing, and that energy triggers an expanding region of space, then suddenly that region blows up, and that creates a lot more energy because you have all this energy, gravitational energy of expansion. So you have more energy coming out of nothing. So it's strange. The universe doesn't have a fixed budget, especially in the early universe. It has the possibility of producing a colossal amount of energy from nothing. And once that space expands and, to a certain point, and then the expansion stops, or actually slows down to ordinary expansion. So you go from super rapid expansion to an ordinary rate of expansion. There's a whole lot of energy that's released, and that turns into the form of particles. And that's where the particles we see around us was produced. And that is called the process of reheating. And that is a standard model of inflation, which most cosmologists and astrophysicists believe in. But since that can happen in, any region of space-time, and it's so easy to happen, so easy to transpire, that's why many people who believe in inflation also believe in the idea of internal inflation, which means you have all these bubble universes, and we're one of many bubble universes out there.
Amazing. These words that you throw out there, I mean, in science, they have technical meaning. But to the average person, when you say nothing, you're just picturing, nothing. And you say, there's vacuum energy. It's like, that's not nothing. There's actually something there. So they would want to, just take the vacuum energy out. You don't get that either. But maybe you're saying you have to start somewhere. And as far as we know, there is no such thing as nothing, no thing. there's vacuum energy at the very minimum, something like that.
Yeah, it's hard to say, vacuum without saying, well, what is a vacuum? You say as empty as possible. So the idea of nothing in space is really, according to quantum physics, an unrealistic idea. So we really don't have in quantum physics complete emptiness. We have as close to empty as possible, which involves all of these quantum fields that are popping in and out of existence. So that's as close to nothing as we can get, but it's still something.
Yeah. Yeah. I mean, this whole idea of nothing, just riff on that for a minute. No thing. Well, you've just identified a thing that can't exist. So you actually have an idea of nothing, which itself is something. So, again, we're limited by cognition, language, the structure of our brains, how we think of concepts or whatever. There's some epistemological wall we're going to hit when we go back, in which at some point I don't even know what I'm saying when I say no thing, right?
Yeah, well, it's funny that things go around in cycles. And in the 19th century, with the idea of electromagnetic waves developed by Maxwell, almost every physicist said, well, there must be an ether out there because waves can't travel in sheer nothingness. You must have something that is waving, something that is vibrating for light to pass through, just like sound needs air or another material, light needs something too. So until the early 20th century, everybody believed that there must be some ether out there. And Albert Einstein radically said, well, let's just ignore the idea of ether and dismiss it and just assume that there is sheer emptiness. And he believed in the idea of sheer emptiness except for geometry, this idea of flat space-time or curved space-time, but there was no material there. But now physicists would say, hey, wait a minute, it's really not empty. There is something out there, and that's the vacuum energy. So we've gone full circle. They won't call it the ether because that's passé, but it's vacuum energy.
Oh, that's so interesting. All right, let's move beyond just the bubble universes that we've been talking about. What are some of the other versions of the multiverse?
Well,
you have a taxonomy in your first chapter.
Well, as I mentioned in my book, the term multiverse greatly precedes modern physics and was introduced by William James, who was trying to describe the idea of a universe that is agnostic to good and evil, doesn't make up its mind as far as good and evil is concerned, and has these two qualities and completely indifferent, impartial, and he called that a kind of multiverse. But of course, that's not the modern term. The modern term came about starting in the late 20th century, and that was triggered by proposal by Hugh Everett, who was a graduate student at Princeton, and he was there in the late 1950s and working with a great physicist called John Wheeler, who was open to all these radical ideas as long as they had some connection with physics. He called it radical conservatism, the idea that you start with the laws of physics, but then you try to push them as much as possible. And Wheeler was perplexed by the idea that in standard quantum physics, you need an observer. And Niels Bohr's model, called the Copenhagen interpretation, imagines somebody looking into a box or observing a box, a black box, and just saying, well, I take a measurement, something comes out, and that's reality. And a lot of people were disturbed by that, even at that point, because the question is, why not consider the fact that human beings are made of atoms too? Why should human beings have their own powers to observe, their own properties? And after all, they're part of the universe too. But Niels Bohr's model, as codified by another great physicist, John von Neumann, imagines somebody taking a measurement and a wave function collapses and turns into physical reality based on that measurement. And depending on the decision made by the observer, the collapse can happen in different ways. Well, somebody who was very skeptical of that idea was Hugh Everett, who probably went to one of Einstein's last talks where Einstein said, well, in quantum physics, and Einstein was very dubious about quantum physics. He said, well, what if a mouse tries to observe something? Will the mouse trigger it to collapse? So Einstein was trying to make fun of the idea of humans causing things to collapse in quantum physics. He thought that everything needed to be perfectly objective and deterministic. And Everett heard that and was really influenced by that. And there were other people around that time that started talking about this idea of coming up with a comprehensive model that doesn't include humans, including the physicist David Bohm and so forth, who had different ideas. And Everett at one point just said, hey, wait a minute. What if a quantum state, which has multiple possibilities, multiple values, never really collapses, and it's connected in some ways to our quantum state, and we're all part of the same universal quantum wave function. So everything is connected, and nothing collapses, and everything just proceeds. Well, if somebody takes a measurement, let's say they're trying to measure the position of an electron, and it could be to the left of a detector, to the right of the detector, in the middle, somewhere, that the person who's measuring it does not collapse the wave function, but rather also has those three possibilities. So one version of them experiences the electron being to the left of the detector. One version experiences the electron being to the right. One version experiences the electron being in the center. And those three versions bifurcate. They don't know about each other, and they proceed for the rest of their lives to believe that they are correct. And there's no way that they can communicate with each other. So Everett kind of talked about it using the analogy of an amoeba or a single-celled organism splitting, and that if it had some kind of intelligence, each version would say, well, I'm the original amoeba. And the other one would say, no, I'm the original amoeba. But if suppose there was a barrier and they couldn't communicate with each other, they would each be vain enough to think that they were the original one. Similarly, we're bifurcating all the time, according to Hugh Everett, but we just think this is the only universe because there's no way for us to have access to the other universes. Now, another physicist who received Everett's paper was Bryce DeWitt, very hard-headed physicist, believed in objective reality, got the paper from Hugh Everett, said, hey, wait a minute, I don't experience this. This can't be right. And then Hugh Everett said, well, do you experience the world turning? Do you feel like you're spinning around? And Bryce DeWitt said, touche, you're right. Not everything in reality is directly experienced. So maybe your proposal's correct. And that between 1957 and around 1970, Bryce DeWitt thought about these ideas and finally was courageous enough to publish an article in the physics journal Physics Today, which was very influential. And he published another article about it and dubbed the model the many universes interpretation of quantum mechanics, which soon became the many worlds interpretation of quantum mechanics. So Bryce DeWitt was a very respected physicist. He promoted these ideas. Meanwhile, Hugh Everett quit physics because he was really frustrated that no one believed in his ideas and went into the defense industry and was still in the defense industry when the ideas really took off in the 1970s and 1980s, and finally made a triumphant speech at University of Texas in the 1980s, talking about his theory, and that was very well received. But sadly, he died at a fairly young age and isn't around today to talk about his theories. And Bryce DeWitt passed away about 20 years ago also, so isn't around to talk about this idea. But it's taken off because of other physicists who promoted the theories.
Huh, interesting. Yeah, I remember reading all those books, the Dancing Woolly Masters and the Tao of Physics and the Turning Point. Fritjof Capra, I really like him. He was on the show. But there's something about this because they want to say the observer is conscious, right? So consciousness has some role in the physical world. But your point is that it could just be a camera or a machine that's doing the observing. So there's nothing sentient about the observer.
Yeah, so the many worlds hypothesis does not come down on one side or the other about whether or not real consciousness exists. I mean, consciousness separated from the material world. So you can believe it's a separate substance. You can believe in souls. You can believe it's completely determined by your material structure and so forth. It doesn't really say anything about that. But what it says is no matter what this thing is, that gives us the illusion or reality, whatever, that we can take a measurement and decide on the measurement, it doesn't make any difference because our reality is splitting all the time anyway, and that has nothing to do with the decisions we make to affect, what happens to the things that we observe.
Yeah, I remember reading one of Michael Crichton's novels, I think it was Timeline or something like that, where his Feynman-like character talks about the double slit experiment and how this allows you to then travel back in time to this other, but it's not really your world earlier in time. It's another world it's really close to your world, but it's not the same, right?
Well, we really don't know. That's hypothetical, but in recent years, there have been a lot of speculation about the idea of traversable wormholes, and physicists have shown that if you set up a traversable wormhole in the right way, a wormhole is a little bit like a black hole, but its traversable wormhole is designed so that you can pass through one end called a throat and a sort of mouth, pass through a throat and end up possibly in another region of the universe or another universe altogether. It's all hypothetical, but you can rig it up so that you can travel back in time in our universe. So the debate is what would happen to the idea that you go back in time and try to do something to prevent yourself from existing, which is called the grandfather paradox. And suppose you went back in time and, not to be morbid, you just convinced your grandparents, that they weren't the right people for each other for some reason. Or like, Marty in Back to the Future
Right.
somehow interacted with their parents and prevented themselves from existing. What would happen? Well, would you create a paradox? Would the universe just blink out of existence? Or would something prevent you from doing that? Or would it create a new universe, a new branch of reality? So there's all sorts of science fiction speculation about that. But since we can't really travel through time into the past, we really don't know. So it's hypothetical. It's fun to think about the idea of going back in time and creating branching universes. But it's something we really don't know if that's possible or not.
Yeah, I love this. You included Stephen Hawking's little invitation to the time travel party. You are cordially invited to a reception for time travelers, hosted by Professor Stephen Hawking, to be held in the past at the University of Cambridge, Gonville and Caius College, Trinity Street, Cambridge, at 12 noon Universal Time, June 28th, 2009. No RSVP required. That's really funny.
Oh, yes.
So this idea of what did he call it? The conjecture protector or something like that? What was
Chronology protection conjecture.
Yeah. So, but that almost sounds like a force that's preventing you from time traveling. But wouldn't it just be that by the second law of thermodynamics and entropy, everything is it's one directional. There's an arrow to time. So you'd have to redo every single atomic molecular interaction of everything that happened all the way back to wherever it is you want to go. So let's say you traveled back in time. You're at the beach. There's a sandcastle, and you've made it really nice. You want to travel back, or it's now washed away, and you want to travel back in time to where it was nicely structured. Somehow the universe would have to reduce just the opposite of entropy. It'd have to be extropy to put all those sand grains back to the way they were. And just, you could use any example. I was thinking of this when I was reading your book. If I travel back to my childhood, to my parents' house where I grew up, well, that house is still there, but it's been remodeled a bunch of times, so it'd have to be unremodeled over and over back to every single molecule and grain of sand and paint and so on. This is just not possible in the universe we exist in, right?
Well, it's interesting because there are a lot of theories in physics that seem to be ironclad, but they contradict each other. So that's the fascinating part about modern physics. What is fundamental? So some people might conjecture that the law of non-decreasing entropy is somehow fundamental. So Roger Penrose talks about trying to find a way to build in entropy into general relativity, because in general relativity, Einstein's theory, everything is completely reversible. And also time is almost on equal footing with space in Einstein's general theory of relativity. So Einstein's masterpiece, his general theory of relativity, which has been shown experimentally to be correct in all tests so far, says that theoretically you can travel through time as well as space, because you look at the universe as something like a block universe, and you don't really have to distinguish between time and space. They're all coordinates, and you can do these funny rotations where you switch space to time and time to space, like in the vicinity of a black hole. Suddenly, the time axis and the space axis, one of the space axes, switch places. So from that perspective, there shouldn't be a law of entropy from pure general relativity, because time is on par with space. In Penrose's modification of that, there is a reason for entropy to start off as zero at the Big Bang and end up very high. And he has another idea called the conformal cyclic cosmology, where suddenly the universe is reborn again and entropy goes back down to zero again, so everything can cycle, which is very interesting. But particle physics does not necessarily distinguish between the past and the future. So there are a lot of aspects of physics that do have an arrow of time. There are aspects of physics that don't have an arrow of time. So the question is it an illusion? Is it fundamental? Is there a way to reconcile all the different versions of time and come up with a unified theory? Those are big questions in modern physics, and no one really has the answer today.
Well, amazing. In the block universe theory, the universe is predetermined, right? If you just have this block, say a loaf of bread here, that's the entire universe from Big Bang to present or future. And you just dive into one of them. Let's say you're the deity, or you're Maxwell's demon, or whatever that is. Leibniz's demon, whoever that was. And so there can be no free will. This is how I enter this conversation, because it's already been determined. Yeah. You just don't know what the outcome of the movie is, but the deity outside can see what the ending and is, something like that. Is that as legitimate a theory of causality as that the universe is not predetermined? It is unfolding as we go from one moment to the next. And with entropy, there's a directionality arrow to time.
Well, it's the opposite to what the band Rush suggested when they sang "I Would Choose Free Will" in one of their songs. Right. But Einstein clearly said in one of his final letters that he did not believe in free will, that the past, the present, and the future are all equally real, and that time is an illusion. That's what Einstein said. Well, Einstein wasn't always right. And his good friend Max Born, the person who coined the term quantum mechanics, said, "Hey, wait a minute, Albert. Does that mean that there's no such thing as free will? That sounds pretty oppressive to me if you're saying that this deity, scientific deity that Einstein talked about, said that everything is determined for all time. That doesn't sound like a type of world I'd like to live in," said Max Born. I'm paraphrasing. But he wrote to Einstein and said, "I really think that you need open-endedness." And he liked quantum mechanics, not because it included free will, but it included the possibility of free will. So Max Born liked that idea. And so there's a debate about that. If you had a strictly block universe, that's right, it would be completely deterministic. But, a a lot of modifications have been made to that. And in fact, in the 1950s, when the first physicists were trying to unite quantum theory with general relativity, one of the first things they did is said, hey, this loaf of bread, that's all very well and fine, but that's not something we experience. Let's slice it up. So they found a mathematical way of slicing up the loaf of bread so that it's one slice at a time, which is the way we all experience the universe, one slice of time, one moment at a time.
Yeah, the idea of free will is the question behind it is, could you have done otherwise? So you have this idea of you rewind the tape and play it again. Well, as Dan Dennett pointed out, if it's a read-only memory tape, then yeah, it's going to be exactly what it is because it's just a recording of what actually happened. But you can't rewind the tape. That is to say, going forward, no circumstances for whatever it is you're choosing will ever exactly be the same. And furthermore, you're a participant in it, and you're aware of what happened last time when these circumstances were similar, and now here they are again, close to that. But I remember I made the wrong decision last time, so this time I'm going to do this other thing, knowing what happened last time. So you're a participant in the universe.
Well, that brings up the cultural idea of the multiverse, which is very different from the scientific idea. The cultural idea of multiverses is what would have happened if I made a different decision? Like, so what would happen if instead of the job I have right now, I was washing dishes for McDonald's, or I guess they didn't use dishes, but, tossing paper plates for McDonald's, then we wouldn't be talking right now unless you were driving up to a McDonald's. But, if I made that decision or any decision, will my life be better, worse? And we all wonder about these what if scenarios. And that's why a lot of books about alternative universe ideas or multiverse ideas play on that idea. What would happen if the South had won the Civil War? What would, the United States be like today? What would have happened if Hitler had defeated the Allies, which, of course, is a premise of Philip K. Dick's great work, The Man in the High Castle. So a lot of great science fiction speculates about different branches of reality. And a lot of movies today talk about this. For example, Everything Everywhere All at Once, which won a record number of Oscars and was a very imaginative movie, imagines what would happen if somebody who runs a laundromat, Evelyn, could picture and even encounter and experience all of the other realities where she had a different path in life, such as becoming a singer, becoming a chef, becoming a martial artist. And somehow she manages to incorporate all of these properties into a same person, which is a really weird idea. Now, no scientist today, as far as I know, talks about accessing these alternatives and saying like, well, we're developing a portal to a reality in which, for example, Donald Trump did not win the election in 2016 or something like that. Nobody is talking about that. People can imagine it, that they can speculate about it, but these are ruminations. These are fanciful things. They're not connected to science, which is a problem for scientists to embrace multiverse ideas, because some people in the general public think that what they're advocating is the idea that we can access their alternative realities and that there are, multiple Spider-Man, like, Into the Spider-Verse suggests, or multiple versions of us that we can talk to and access. And none of the scientific ideas of the multiverse imagine a way for us to meet our doppelganger, except maybe the very far-reaching idea of traveling back in time in a wormhole and somehow meeting yourself that way. But most of these multiverse ideas says either all other universes are completely inaccessible because they're incredibly far away from us, multiple billions or even trillions of light years away from us, or they're in this other quantum branch of reality that we can't really access.
Well, I like the idea of counterfactual causality, what if, because it does allow you to play with different scenarios in which you remove one effect, you remove one cause to see how the effect might change. So what is it that determined the outcome of the Civil War? And some people put it at this moment before the Battle of Antietam-Sharpsburg, when things were kind of hanging in the balance. And I think Lee's plans were wrapped in a cigar box or something, and they fell out of the bag of the courier on his horse, and the Northern troops found it. And so McClellan got Lee's plans, was able to thwart his invasion and so on. And that was their turning point. But of course, that depends on when in the timeline the crucial contingent event happens. If that happened during, I don't know, Sherman's March to the Sea, when it was pretty much a done deal what was going to happen, probably wouldn't have made any difference at all. But at least as a thought experiment, which is legitimate in physics, right? I mean, Einstein did famous thought experiments. Yes. That's okay. Kind of, it's like that movie you were talking about, films along this line, Sliding Doors with Gwyneth Paltrow.
Right.
I like that because, just that one moment where she's coming down the stairs and there's somebody coming up, a mom with a pram or a baby carrier thing, and she has to go around it. And that split second means she misses the subway as the sliding doors close, or she makes it and then she finds out her boyfriend is having an affair. So there's two different scenarios. She finds out he's cheating on her, or she doesn't, and then it has different outcomes. Of course, you're correct. We can't play it both out. One happens, and then life goes on, and it just seems like that's the way it had to be. However, that turns out. So we're really talking about two different things. What's theoretically possible? That's not theoretically possible to have both of them. But it's almost like that. My favorite example from Tim Minchin, the singer-songwriter. He has this amusing song about his wife. If I hadn't met you, all these wonderful things wouldn't have happened, right? And he goes through the first half of the song is all about that. And he says, of course, if I hadn't met you, I would have met somebody else. And maybe she'd have been taller than you, but not as good looking, more athletic, but not as funny. And whatever had happened, you'd go, well, that's the way it had to be. And look what all the contingent events that led me to meet you, but you'd say that about anybody you met, right? So whatever happens, we look back and go, oh, it's unbelievable. I turned left instead of right, or I took this course and met that professor instead of this other one. I ended up in physics instead of psychology, whatever it would be. You inevitably look back and go, well, it had to be that way.
Yes. Well, I love the film Sliding Doors. I saw it again recently. I wrote an article, which should be out by the time this is broadcast, for New Scientist about the best multiverse movies, in my opinion. So I watched a lot of multiverse movies, and I ranked Sliding Doors as up there. And the question that it raises many questions. I don't want to give too much away in case people haven't seen it. But the question is, if we feel lucky about something, does that necessarily mean that was the right branch or the best branch? So if you just make a subway train and you just about make it, you say, oh, wow, I'm so lucky. But, of course, if sadly enough, that train was one that was in an accident a few minutes later, you'd feel, oh my God, if only I didn't make it through those doors, I wouldn't have been on this train. So it's sobering to think that sometimes, some moments you think, oh, I was so lucky for that, might have led to, branch of reality, if there is such a thing, which ended up with a very poor outcome. Whereas things that you thought were unlucky, like missing a train or, not meeting someone or getting rejected from a job, turn out to be the best course after all. We just don't know.
Yeah, Seth MacFarlane, the creator of Family Guy and the Orville and so on, tells a funny story, not a funny story, but a potentially tragic one, where he was out partying in Boston on September 10th, 2001. And he was sort of hungover, and he missed his flight back to L.A., which was the flight, one of the flights that went into the World Trade Center building. So he would have been on that plane. So he looks back, whoa, good thing I was hungover. It's like one of those weird contingent events.
Mm-hmm. Yeah, it's frightening, and that's why the idea of, in culture, the idea of a multiverse in which all these outcomes are out there, these other outcomes, is truly fascinating to us
But now,
because
so in one of the multiverse versions, all those things do happen. Every possible thing can happen, right?
well, in a scientific version, the Everett hypothesis, all the quantum possibilities happen, but the differences are so subtle that we can't really say that for a particular event that was life changing. So, for example, if your job is to measure a blip on a screen due to whether or not an electron is going one way or the other way, one version might see one kind of blip and the other might see another kind of blip. So it'd be nothing to write home about unless that turned out to be, a pivotal moment in history. You made a discovery based upon that one experiment, which is unlikely since most discoveries are made, from experiments are made from multiple experiments. So it's not like in the Everett hypothesis, you'd have one branch in which you're, wealthy and the other branch, which you're poor, as much as the self-help people who, exploit the idea of quantum physics to try to sell their products and say, okay, you can use quantum physics to get rich, or you can use it to live forever or whatever, as much as, some hucksters might try to purport that. In fact, the differences between the two quantum realities, even in the Everett model, are extremely subtle.
What are some of the other of your favorite multiverse movies while we're on it?
I really like Run Lola Run, Donnie Darko. Back to the Future has a kind of multiverse scenario in it. 12 Monkeys kind of imagines, whether or not reality is flexible or changeable. So it's still, but at the end of the movie, a bit of an open question. The Matrix imagines, alternative realities based upon this idea of artificial intelligence creating a universe. There's Everything Everywhere All at Once, which I like conceptually. And I recently saw the first Into the Spider-Verse movie, Into the Spider-Verse, which I loved. And that's a really fun movie about the idea of multiple Spider-Men. So that's a really cool one.
I forgot about Run Lola Run. That was similar to Sliding Doors, if I recall.
And I think it came out the same year, so something was in the air about that.
Yeah. All right, let's talk about multiple dimensions and the multiverse. Here you have, if I can show this on the camera, you have the kind of line land from flatland, and then I guess this would be flatland, and then this would be sphere land or cube land. And this would be, I don't know what you'd call that, but
hypercube land.
Could you actually make that? Kind of washed out there, but could you actually make something like that in 3D, or are we talking about something that you can't really make in 3 dimensions?
Well, you can look at a projection of the 4th dimension onto a 3-dimensional object. So one way of envisioning the 4th dimension is to imagine a shadow of it onto a 3-dimensional object, which is just like we can take a hollow cube and hold a light up to it and form a shadow on a wall.
Yeah, I could do that. So there would be the shadow.
Wow. Instant experiment. Yeah, so this is what Plato imagined way back when with his cave allegory. He imagined prisoners in a cave, and they have no access to the outside world, and they see shadows of people walking by, and they think the shadows are reality. So maybe the 3-dimensional things we see are somehow shadows of a higher dimensional reality, which is kind of weird to think about. But another way of thinking of the 4th dimension is to imagine 3-dimensional things changing in time. So if you took a balloon and you started blowing it up bigger and bigger and bigger, and you somehow cemented together all the different times of the balloon. So you had tiny balloon, a little bit bigger balloon, a little bit bigger balloon, giant balloon, and then deflating balloon, and so forth. If you somehow linked all those things together, you would create this 4th-dimensional object, which would be representative of an expanding and then contracting balloon, which is pretty weird to think about too.
It's really weird, but multi-dimensions are weird. So again, it's back to this math versus, physical reality. How do you know that there are multiple dimensions? Is it just an extension of the equations of the math that proves they have to be there or something like that?
Well, there's extensions, there's theoretical ideas, which a lot of theorists believe, but then experimentalists said, how do you test these ideas? And there's some ideas that gravitation leaks into a higher dimension, which explains why gravity is so much weaker than the other forces. Gravity is incredibly weaker than the other forces, which you can see using a simple experiment. If you try to pick up a paperclip with a refrigerator magnet, and then you launch that as a battle between the Earth's gravity and the refrigerator magnet's magnetic force, the refrigerator magnet will win. And so it beats the Earth, which means that Earth's gravitation is overpowered by the magnetism of a refrigerator magnet, which shows how weak gravitation is compared to magnetism. And anyway, theorists came up with this idea that gravity leaks into a higher dimension. Well, how do you prove that? Well, maybe through collision experiments, some energy is missing. And if you reel out all other possibilities, maybe that energy leaked into a higher dimension. So there have been tests of that, tests of resonances, which is something like when you strike a note on, let's say, a xylophone, you might hear higher tones. So maybe you might experience higher energy resonances from a higher dimension. And all these weird ideas and tests in the Large Hadron Collider have been trying to determine whether these are real or not. And so far as we know, all the tests came out negative. But theorists still won't give up and they say, well, let's propose more tests and so forth. So there are ways of possibly testing these ideas. And theorists have not given up yet on the idea of unseen higher dimensions.
So weird. I mean, so much of this stuff is weird, but maybe there's just different ways of coming at the nature of reality. In your previous book, I was looking at my notes of that. You talked about the friendship of Wolfgang Pauli and Carl Jung and their correspondence. I mean, that itself is a weird thing, but maybe we should be more open to, I don't know, gurus or people that do magic mushrooms or ayahuasca or, I don't know, people that try to access reality through different means other than science. Maybe that's not totally crazy. I mean, as skeptics tend to say, oh, that's just a bunch of baloney. But, maybe it's not entirely. Maybe we shouldn't be completely closed off. Given everything you've just said, it's like, how do I know any of this stuff is true?
Well, we need to be humble, but we also need to come up with models and, if a model is, perfectly valid and testable within its limits of observability, but there are also things out there that are non-observable but still match the model, then we might conclude, well, even though there are non-observable things, it's still a good model. Like, for instance, we know that the Earth has all this material inside it, as a core and various layers. And some of that has been tested, but we can't say that every inch of the Earth's interior has been probed and tested. So we just kind of deduce that, the Earth must have solid regions, liquid regions, and so forth from the tests we can do, and just assume that that's true for all of Earth's interior. So we often deduce things from what we can observe. But that doesn't mean we should talk about things in which there are no ways to test it, or things that testability has turned out completely negative so far, such as, for example, the idea of telepathy. Nobody has come up with, experiments that have conclusively shown that telepathy is valid. So most scientists or physicists would not consider that within the realm of science.
Yeah, this is my beef with the words paranormal and supernatural. Those are just words. we're using to describe something we don't understand or some unexplained mystery, or there's nothing to explain. It's just an artifact of confirmation bias or whatever. And so, like, I use the example of dark energy and dark matter. You guys don't mean that as an answer to a problem. Those are just linguistic placeholders until you figure out what it is that's, causing the galaxies to hold together or the universe to expand at accelerating rate and so on. So it comes down to what those words actually mean.
Yeah, to go back to your quote from Donald Rumsfeld, those are the known unknowns. So
yeah,
we know that something's out there, we just don't know what. So we keep doing tests. We're not satisfied by having unknown things out there.
There is a theory, this sort of quantum consciousness theory, where the collapse of the wave function inside neurons, inside the microtubules inside neurons. This is Stuart Hameroff and Roger Penrose's idea, that somehow that wave function leaves my skull and goes into your skull, and we can read each other's minds or whatever. I don't think any of this is true because there's nothing that needs explaining. People can't read each other's thoughts. But if they could, and that was the explanation, that wouldn't be paranormal or ESP. That would just be, I don't know, quantum physics or, quantum consciousness or something like that.
Yeah, there are physicists who speculated about that, but I have to say, knowing people in the psychology, neuroscience community, that idea really hasn't taken off in neuroscience and so forth, which is more using things like functional MRIs to try to pinpoint, where the brain enacts certain processes.
Do you have your own theories of consciousness? How you explain it?
I call it one of the greatest mysteries. So I don't speculate about it. I find it, every day I find it amazing. And sometimes, when I'm driving to work, I kind of test it. I say, well, I like to plot out on my own. I know I'm a minority these days. I don't use a GPS. I just kind of figure out the route or take the same route. And sometimes I just say, just for the heck of it, I'm just going to, take a different route today or something. And then I feel kind of like, well, at least in my own illusion, I've exercised my free will and exercised my right to choose the route. So, so that's kind of important to me, to feel like I'm doing something with free will, even if it turns out to be false.
Well, I think that, again, is one of those, I think consciousness, free will, and God are three, and why there's something rather than nothing, are these kind of known unknowables. In part, not that we can't solve it because it's really hard. I mean, it's conceptually, I don't know, misframed or presented in a way that can't be explained. I mean, if the word means something, volition, freedom, free will, but we live in a determined universe, then what are we even talking about? It's not possible. But it's an illusion, and it's a useful fiction. You certainly feel free. I don't know any determinist that actually acts like they're determined. They act like they're free, like everybody else.
Yeah.
Right. And I think, again, back to my explanation earlier, if the universe is not predetermined, my theory depends on that, then you can't replicate the past exactly. And you are part of the moment to moment, participating in the kind of self-determined universe, you might think. And I think consciousness is also one of those misconceived ideas that, is my read the same as your read? It suggests that almost a dualism, like there's a little homunculus in me, a little mini me that can, a little ghost in the machine that can go over into your skull to see on the Cartesian theater, as Dennett calls it, of your mind. And you're like, oh, look, his red looks like my red. This is a ridiculous idea. This is not possible.
Yeah. So as a physicist, I don't really speculate about, areas in neuroscience, psychology. And I also think that consciousness is one of the greatest mysteries. And I'd be really shocked if somebody came up with an explanation. And when people talk about trying to program artificial intelligence to have consciousness, I think, wait a minute. Even if some kind of network said, I am conscious, why would we believe that? And you could very easily write a simple program, any of us could do it, that just says, hello, I am conscious. And like, why believe this program? And if it's a very sophisticated program, incredibly sophisticated that takes in all this data and still says, hello, I am conscious. Why would we believe it in that case even?
Yeah. Well, that's the other mind's problem. How do you know that I'm sentient and conscious? You don't.
Yeah.
The philosophical zombie, you're the only one that's sentient. Everybody else is a zombie. No one's
Yeah.
home.
I just kind of assume that other human beings are similar to me, which is, a very important working assumption to get through life, that everybody is conscious. But I would not assume that an algorithm is conscious because I have no experience with that.
Yeah, my example is when Watson won Jeopardy. I'm a big Jeopardy fan, so that was a big moment. Does Watson know that it won Jeopardy? Does it know that it beat the great Ken Jennings, the greatest Jeopardy player of all time? No, it doesn't even know it's playing Jeopardy. It doesn't even know what Jeopardy is.
Yes.
Right? It's just an algorithm scraping Wikipedia mostly, I guess, to get the best answers.
Oh, yes. Right. Yes. So we don't know how to test that.
Okay, another the last known unknowables: eternity and infinity. I mean, what do you guys mean by these words, and how can we ever wrap our minds around that?
Well, in my book, I try not to use the word infinite or eternal, unless someone else used that term. Like if someone talked about eternal cycles or a universe that's infinite, that's very speculative. So I like to use the word unlimited or, testably unlimited or, just because we really don't know. It's hard to wrap our minds around something that's infinite. But I do mention in one of the chapters of my book this idea by Hilbert of a hotel with an infinite number of rooms. And if that were possible, then even if all the rooms were technically full, that by moving one person over to the next room and then the next person to the next room, you could theoretically accommodate an unlimited number of people, which would be very interesting. And in a way, the theoretical foundation of quantum physics, which is called Hilbert space, is something like Hilbert's hotel with an unlimited number of rooms, which is really odd. But in some aspects of quantum physics, you have these spaces which have an unlimited number of dimensions and an unlimited number of possibilities.
So weird. Yeah, I was watching one of those Netflix documentaries on eternity. I forget what it was called, but Adventures in Eternity or Infinity or something like that. And it's just so bizarre. Like everything that could possibly happen will absolutely happen, because if you have no limit to time or space, and it's like, okay, again, it's like, why is there something rather than nothing? At some point, I don't even know what these words mean.
Yeah. Well, I expect to be back on your show again and again.
When you figure it out.
Throughout eternity, even if you don't invite me.
That's right. We will have this conversation again.
Yes.
Yeah. So, I mean, so much of this also seems context dependent. This is 21st century physics right now. You're giving us the best in your book, what we know now. I mean, if you wrote this book 100 years from now or 500 years from now or 5,000 years from now, I mean, it could be completely different. And you look back and go, look what those people thought back in the 21st century, early 21st century. This is crazy what they believed. Something like before Newton, how the people before Newton, or just say in the late Middle Ages or something, thought about physics and the universe and stuff. It's just so completely different than ours.
Yeah, and I'm hoping that people in that far future still read books.
Yeah,
so that's an open question too.
I suppose so.
Hopefully that will be that art of reading will still be preserved.
Or it'll just be beamed into our chips that are in the brain if we're not completely AI ourselves.
Yes.
All right, Paul, this is great stuff. I love the book. I love all these big topics. What are you working on next?
Well, as I said, I'm releasing, I guess I just finished it, but an article about the best multiverse movies. But right now I'm kind of taking a break from thinking about new projects because I'm excited about this new book, The Allure of the Multiverse.
Yeah, nice.
And I'm doing, a number of, events, in-person events, mostly in the Pennsylvania area if you're in Pennsylvania, but hopefully in other places too. And I'm very excited about the release of the book and the reaction to it. The Allure of the Multiverse.
Here it is again, The Allure of the Multiverse. Go get it. It's a great read. I think the audio, do you read the audio version?
No, it's another Paul Woodson.
Oh, okay.
I don't know him, but he's a,
right.
a voice actor. So he's
nice.
a Paul in another universe where I had a different last name and had a different occupation, voice actor. Yeah.
That's great. All right, Paul, that's good. Thanks for coming on to talk about this.
My pleasure.